Hi guys, welcome back to my channel. So in this video I will show you guys how you can convert such a big number into a single precision, okay, using the data structure for the single precision. If you want to know using the normal data structure like this one, so I've already made a video on this one. I did many problems on that, so you can check out the previous video for that one. So for this one we are using the single precision, and I remember the teacher saying this is going to be a very important question in the exam, and you basically have to memorize this structure, because for the other structure he said he would give you guys, but for the single precision he said to memorize this structure, okay. But yeah, and the double precision, this is really long, okay, 52 bits. So he said if you want, there is a problem on that in the slides, you can look at it, but he says you don't have to worry about it because it's really long, you know. So okay, so let's go ahead and actually do the single precision problem. So what do? We're going to divide the number the problem into two parts, right? First we're going to convert the 52 into binary, and then the decimal part 0.65625 into binary. Okay, so we have 52, and let's go ahead and convert that into binary. So what do? We're going to divide by 2, right? Since this is in decimal base 10, but we need to convert it into base 2, that's why dividing by 2. So 54 divided by 2, if you don't know, you can use a calculator. So this should give you 27, okay, and we do not have a remainder, so it's gonna be remainder 2. Okay, now we're going to take this number again, 27, and we're going to keep dividing this number that we get over here by 2 until we get a 0 over here, okay. So 27 divided by 2, so that's going to be 13, remainder 1. Okay, because 2 times 13 that's 26, and we get a remainder of 1. Okay, so then we have 13 divided by 2, so we have 6, remainder 1. Okay, and then 6 divided by 2, that's a 3, remainder 0. And what's 3 divided by 2? That's a 1, remainder 1. And what's 1 divided by 2? That's a 0, remainder 1. So now you can finally go ahead and stop, okay, because you hit a 0. And I hope this thing is making sense. If anything doesn't make sense, you can always ask me in the comment section, okay. And I don't know if I explain well or not, because like if you don't like any of my method of explaining, or if anything is not clear, you can always let me know in the comments, because like I said, like it's written on my channel, I'm a student like you guys. I'm not a professor, so I might not explain things very well. So if there's anything that I can improve and you don't understand the way I explain or anything, you can let me know in the comments below. Okay, so here we have this decimal over here, so we need to convert this into binary. So since it's a decimal, here it was a whole number, that's why we were dividing by 2. Here it's a decimal, so what we're going to do, we're going to multiply by 2. Okay, so we're going to keep multiplying by 2 here. So this one we get 1.3125. so now we're going to take this decimal part only, so we take 0.3125 and times 2 again, we get 0.625. Now we're going to take this 0.625, the decimal part, times 2 again, 1.25. We're going to keep repeating this step until we hit a whole number, okay. Okay, so now the decimal part, 0.25 times 2, we get what? 0.5. 0.5 times 2, and we finally get a whole number. And since we get a whole number, which is like 0.0, you can say 0.0, so we stop. Okay, so now let's go ahead and actually write these numbers out into binary. So 54 in binary. Okay, so we have 54. I want to use another color. Let's go ahead and use pink. Okay, so this number, we're starting at the top, right? We're gonna write 0, 1, 1, 0, 1 1. Okay, and then point, what do we have over here? We're going to look at these values that you see over here. Okay, for the whole number we look at the remainders, but here for the decimal we look at these numbers. Okay, so we have 1, then we have a 0, then we have a 1, then we have a 0, and then we have a 1. Okay, so this completes our problem for converting this into binary, right? This number, this ugly number that you see over here, this is this thing in binary. Okay, so now what's the next step? So the next step is basically to normalize it, right? So let's go ahead and normalize this number. So normalize means we have to move this decimal place. So 1 2 3 4 5. Move this decimal place by 5, right? Okay, so this number is going to become 1.10110101001, okay, times 2 to the power of 5. Why 5? Because we moved the decimal place by 5. Okay, so this is your number normalized. Now once you have normalized, what's the next thing? We need to simply pack everything, right? So let's go ahead and pack everything. It's ugly. So we have sine, we have mantissa, and what do we have? It's gonna be bigger, so let's go ahead and make something big. Sine, mantissa, and exponent. Okay, so here we have for the exponent we have 5. Okay, so we have 5 for the exponent. Do we have an excess over here? We have an excess of we have an excess of 127. Okay, so we need to add the excess into the exponent. Okay, so we have the exponent as 5, but we need to add the excess to it, which is 127, right? So let's go ahead and add this. So if you go ahead and add this, so it should give you 132, right? And since it's in decimal, we need to convert this into binary. Okay, and this is gonna be a long process. So if you go ahead and convert this into decimal, so it should give you, okay, so converting this into binary should give you 1. So this is gonna be your answer of 132 into binary. Okay, so once you have written this number, what you have to do, you're going to check how many bits you need. For the exponent you need 11 bits. Okay, so you're going to write this number over here. Let's go ahead and put it over here. Okay, and then we need 11 bits. How many do we actually have? So we have 1 2 3 4 5 6 7 8. We have 8 and we want 11. Oh wait, I guess I was looking at the wrong thing. Oh, I was looking at the double precision. I was supposed to look at the single precision, sorry. Okay, so for the single precision we have 8 bits and we already have 8 bits, so we don't need to sign extend it, so we're good. And the mantissa, and for the sign it's a negative, so we put a 1 over here. And now finally for the mantissa, you see mantissa we have 23 bits and a hidden 1. A hidden 1, that means we're going to ignore this first one that we see over here, okay, and we're going to write whatever we have after it, and we need to make it into 23 bits, which means we're going to add extra zeros to make it 23. Okay, so we have this number. Okay, so we have 1 0 1 1 0 1 0 1 0 1, and we have how many numbers? So we have 1 2 3 4 5 6 7 8 9 10. So we're going to add 13 more numbers. Okay, so I added more zeros, and now it's in 23 bits, and this finally completes our answer.